Okay guys, and that brings us to Lab 7. And in Lab 7 we are doing a lot of Lewis dot structures, bond angles, shapes, dipoles, etc. etc. I would suggest rewatching Lab 7 video. You see that at the very bottom because that kind of goes through and explains all the structural stuff on Lewis dot structures. Or on these molecules. But I'll also show you a quick example of a couple of these molecules. So we're going to go through CO2, H2O, and Zenon Tetrafluoride. So first one is carbon dioxide. I always like to start off by labeling how many how many electrons each atom contributes. So this carbon is going to contribute 1, 2, 3, 4 electrons, and you just figure that out because you just go straight across here. You skip this whole section to find out how many valence electrons they have, as you won't be dealing with any of these in your general chemistry, or I don't think you'll be dealing with any of these in your general chemistry class. Or you will be told how many, what the charge on them is. So anyhow, we've got carbon over here. Carbon contributes 4 electrons, so we'll write a little 4 underneath it. And then each oxygen is going to be contributing 6 electrons, so we'll write a 6 underneath it, but there's 2 of them, so we'll write 6 times 2. And so then I like to add up all of these, so it'll be 4 plus 12 is 16. So we'll have 16 electrons that we need to use up. I start by just simply drawing a skeletal structure. All that means is that you just draw the most basic diagram of what this will look like. Typically your most unique elements tend to go in the middle, and that just means whichever one is not repeated, or carbon will often be in the middle. Hydrogen is never in the middle. You can look up a lot more rules in your books or on the web. But anyhow, let's go through this CO2 example. So we've got 16 electrons. We've used one here. We've used one right there and one right there. So that's 2. One right here and one right here. That's 4. So then we'll need to just fill up the rest of them and see how we're doing. So if we go like this, you want to try to satisfy the octet rules. Okay, so we've got the oxygen is satisfied because it's got 8 electrons. That's what the octet rule says. You can just kind of circle this guy right here. So see, he's sharing 8. Carbon is currently sharing 4, and this oxygen is sharing 8. So carbon is probably going to want 4 more electrons, and if we count our electrons, we have 2, 4, 6, 8, 10, 12, 14, 16. So we've got enough electrons, but carbon does not have its octet satisfied. So this is not going to work out if we do it this way. So we're going to have to try moving some of these electrons around. So how can we get 2 more electrons or 4 more electrons on carbon without losing any electrons on the oxygens? Well, we can take these guys and move them onto our carbon, so that we have something that looks kind of like oxygen, carbon, oxygen. But now we've got, since we've moved those 2 electrons but they're still sharing, we're going to have double bonds. And so then we'll have 2 electrons there, 2 electrons there, 2 electrons there, 2 electrons there. So that gives us, let's see, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons, and all three of these elements have their octet rules satisfied. So we're done. In this case, we will not have a dipole moment, and if you refer back to your lab, it walks you through what is considered to be what sort of arrangements would give you a dipole moment. So here, a molecule will be polar and have a dipole moment if there's at least one lone pair on the central atom and the molecular geometry is not symmetrical. So in this case, we don't have anything on the central atom, and our electrons, and it's a symmetrical molecule anyway, so basically we will not have a dipole moment for CO2. I might not do all of these, but let's go on and do H2O. Once again, we'll start off by drawing the central atom first. Oh, that's an oxygen. Remember, you never have hydrogen as your central atom, and we'll draw a little basic structure for it. Okay, so how many electrons are we going to have? Well, hydrogen contributes 1, so there's 2 hydrogens, so that will be contributing 2, and our oxygen over here will be contributing 6. So that means we have a total of 8 electrons, so 8 electrons, and well, we've used 1, 2, 3, 4, so 5, 6, 7, 8. We've got our 8 electrons, and so we think we are, in this case, oxygen is the only one whose octet needs to be satisfied. Hydrogen is happy with just 2, and the reasoning for that is because in its outer shell you've only got 2 electrons, and that is why you don't need to satisfy an octet on hydrogen. Anyhow, we would normally look at this on our Lewis dot structure and think, hey, this looks like it's not going to have a dipole, because if we go back to our dipole, we see a molecule will be polar if it has if there's at least one lone pair, which we have at least one lone pair, and the molecular geometry is not symmetrical. So this leads us to believe that our molecular geometry would be symmetrical. But if we actually think about the 3D structure of this that we're going to have, so our oxygen will be here. This is going to be a tetrahedral shape, so we'll have one hydrogen coming off right there and another one coming off right here. But now, to do the tetrahedral shape, this pair of electrons has to come out towards us while the other one goes away from us. So hopefully you understand what I'm talking about. That's what all of Lab 7 was about, is figuring out how we could get or figuring out the molecular geometry of these guys. So you can tell right here that our electrons are not symmetrical. So if we try to reorganize this shape, maybe let's move this hydrogen down here and those electrons over there, then maybe we'll have a more spread out type of shape. But really what all you're doing is reorganizing this molecule. You still have a dipole moment because these electrons, if we redrew this, and it's hard to draw in three-dimensional space, but if we kind of redrew this out, this is kind of what it would look like. So we have our hydrogen over here, and our electron pair is actually kind of back, and this is kind of back. That's kind of if we rotated the molecule, or whoops, I've got all too many hydrogens. Well, anyway, hopefully you get the idea of what I'm talking about. If you're still having trouble with this, watch the lab video for Lab 7, and hopefully that will help out understand those 3D structures a little bit better. So finally we've got Zenon Tetrafluoride, and to draw that one we will just be well, first we've got to count our electrons. So xenon is going to be contributing 8 electrons, and tetrafluoride, each one of the fluorides is going to be contributing 7 electrons. So if we draw out our xenon tetrafluoride, okay, this guy's contributing 8, each one of these is contributing 7, so 7 times 4, so total number of electrons is 8 plus 28, and that is going to be 36 electrons. So like I said, always start off by drawing the most unique element in the center, and then drawing out all of your other figures, or all of your other elements. And in this case, if we try to put an if we try to satisfy the octet rule on all of our fluorines, we will find that we've got an uneven number, or not our whole number of. We don't have 36 electrons used in this. We've only got our 8 right here. We've got another 8 right here, 8 right here, and 8 right here. So this only adds up to 32 electrons. We need 36, so where else can we? So we're going to have to put them around the central atom. And in this case, the molecular geometry will be octahedral. And so if you kind of can visualize that, we can actually put those electrons on completely opposite sides, and therefore we have a symmetrical molecule. So there will be no dipole moment on Zenon Tetrafluoride. Okay, so that brings us to Lab 8. This is the PV equals nRT lab that you guys all had to do as a formal. So hopefully everyone did really well and does not need to review this, but in case you do, let's go over some PV equals nRT. So the equation PV equals nRT stands for pressure times volume equals the number of moles times a constant times a temperature. Now the secret to using this equation is that you have to make sure that all of your units are in the same, or all of your variables are in the same units that match up with R. So R can be pretty much anything. I think you guys use R equals 0.082 and your units are atmospheres and liters, atmosphere liters per Kelvin mole. I believe that's what your units are. So there are also other R's that have different units, but I think if you just use this R, you should be fine as long as you make sure to get everything into those units. So let's do a little practice problem. If we have, let's say, a pressure of 730 torr, well, we need to convert this into atmospheres, right? Because that's our unit of R. So to convert that to atmospheres, we know that there are you might be given in the test that 760 torr equals 1 atmosphere. So this will be one of those conversions that you have to do. So 730 torr over 1 times what gives us atmospheres on the top. So well, we want atmospheres on the top, so we're going to want to write atmospheres on the top, and it equals 1 atmosphere for each 760 torr. So this allows these units to cancel out, so your torrs cancel out with your torrs, and you are left with 730 over 760 atmospheres as your answer. So you would need to convert the pressure into atmospheres. If you are given volume in milliliters, you want to convert that to liters. So let's say you're given that it's 730 milliliters. You want to convert, and you know that 1,000 milliliters is 1 liter. So therefore, you want to set up your problem the same way: 730 milliliters over 1 times what gives us liters as our final unit. So we'll want to put 1,000 milliliters on the bottom, not only to cancel out our milliliters with milliliters, but also to get liters on the top. So we can then cancel out our milliliters, so on and so forth. Now you're going to have to be able to manipulate some of these equations, so just be sure that your algebra skills are up to par. So for example, if we are given, let's say, if we are asked what number of moles are in a beaker that has a gas at a temperature of, let's say, 80 degrees C, a pressure of 1.2 atmospheres, and a volume of, let's throw out some number, like, let's say 2 liters. So the first thing is, get everything into those standard units. So we need to convert this Celsius to Kelvin. So that's just simply 273 plus 80, and that will be 353 degrees Kelvin. And I'm running out of space over here, but then we just need to rearrange this equation to find N. And I would suggest that you leave these in variables. So let's say nRT equals PV. We would divide both sides by RT. And then it's simply just plugging in units, because we can cancel out this RT with this RT. And now we've got N equals PV over RT, and you just need to plug in all these units, and that will be how you do a problem. So hopefully that helped on this one, and that will bring us to Lab 9, which unfortunately we skipped.